Great. Hello, everyone. And thanks for coming. As I was already introduced, my name is Hossein and I'm a software engineer and part-time data scientist at Databricks. And I'm really excited to be here. Like my last visit to Seattle was in 2010, and I forgot how beautiful it is. Okay, so a little bit of introduction. That's sponsoring my visit. Databricks is the company that is founded by creators of Apache Spark, and it's focused on making big data. And the way we try to do it is by offering an end-to-end platform for processing data in the cloud. We are very dedicated to open source Spark. We are the largest organization in terms of the commits and code contribution to Spark, and we try to drive the roadmap through contribution and active development. Okay, with that done, this is the outline of my talk. Before I actually go through the talk, I would like to do ask for a show of hands, and please pay attention to this part because it helps me tune the talk accordingly. Please raise your hand if you know about Spark. Okay, almost everyone. And please raise your hand if you are using Spark. Okay, so about half. And please raise your hand if you're using R. Okay, close to 90% is. And now I need to ask for the overlap. Raise your hand if you're using Apache Spark and R. Yes. I mean, not necessarily together. You're a user of both systems. Like you use them day to day or on a weekly basis. Cool. So I can see about less than 10 people. Okay. Okay. So I can assume this crowd is fairly familiar with Spark. So I will not go through details of my section of introduction to Apache Spark. I'll just skim through them very fast. Please feel free to stop me if anything is not clear or you have questions about the the overall Spark. And then I'll get to the second section, which is a deep dive into SparkR and what it is. Okay, so Spark. I really like the platform, and it seems many other people like it. Fortune magazine recently had an article and called it the Taylor Swift of big data, and we loved it. It's very we really like Taylor Swift, and we really like Spark, and the two really resonate. But more formally, it is a general computing engine. It was developed at UC Berkeley and makes the processing of big data very simple. It has interfaces for Java, Scala, and Python. And recently, the last interface that was added is R. And that's why we're all here. And it comes with built-in libraries for SQL, streaming, machine learning, graph processing, and there's active development in all of these. And as you all know, the programming model is based on a core concept, which was Matei's PhD topic, resilient distributed data sets, or RDDs. It's basically an RDD can be transformed to another RDD, and they can be distributed across multiple machines. You can control where it resides in the memory hierarchy, on disk or in memory or an SSD. And they're resilient, meaning that if one of the machines that is participating in an RDD dies or something happens to it, the RDD knows how to reconstruct that portion of itself. Hence the word resilient. So, very quick, I'm going to go through this. A very simple example of log mining in Apache Spark would be loading the data from distributed storage, or it could be a local storage. That gives me an RDD. And then I can do some transformations on that RDD. Here I'm doing a filtering in Python. Gives me another RDD, another transformation. And then I call cache. Up to here, as you all know, everything is lazy. So nothing has really happened. All we've done is telling Spark how to perform the transformations. It hasn't done anything. And then I perform an action, which is the count. And at that point, Spark actually starts doing things. And what it does is basically telling all the workers to read the data from distributed storage and transform it, and then finally cache it. And then at the end, your subsequent actions against that RDD will hit the cached version, so the workers don't have to hit the disk again. So it can be done much faster. Here are some fairly old performance results, and this was how Spark started. This is the original API, and this is how very quickly it could scale to terabyte data sets. Fairly quick time in terms of development, and also fairly efficient. As I said, RDDs are resilient. That means if a portion of an RDD fails, it can reconstruct only that portion. So if you imagine the last stage, one of the partitions fails or goes away, because Spark keeps track of the lineage, it can reconstruct it by knowing exactly what partitions need to be transformed again to get to the lost part. Because things can be cached in memory, iterative algorithms are particularly well suited in Spark. If you have a machine learning optimization algorithm that needs to iterate multiple times, the first iteration, let's say, takes 80 seconds. Subsequent iterations take an order of a second. As a result, comparing it with Hadoop, you can do your machine learning much faster. And that was one of the very early appealing parts of using Spark for big data and data science. Okay, so this is also important to note. Spark could break the terabyte sort record in 2014, and the record prior to that was held by Hadoop. Yahoo actually did that. They used 2,100 machines and could sort a terabyte in 72 minutes. Next year, Spark used 207 machines and sorted that same amount of data in 23 minutes. And at the same time, just to test it, we sorted 1 petabyte in 1 hour, in 4 hours. Sorry, on the same in the same setup. So it definitely scales. You don't need to worry about scalability. The one thing that makes is clear out of this benchmark is that Spark does scale. Okay, so I talked about the libraries. Everyone should probably be familiar with these. Spark SQL is for structured data processing. Spark Streaming for real-time analytics, and MLlib is the machine learning library, and graphics is for graph processing. All of them are sitting on top of the same core engine. One thing to note is that starting off, every one of these libraries was using RDDs. Since Spark SQL was introduced, it introduced a new concept. Initially, it was called Schema RDD, and then because we were talking to the community and we were trying to steal the best ideas, we realized that data frames are actually a better abstraction. So Spark SQL renamed Schema RDDs to data frames and introduced a whole bunch of new functionality to basically make it closer and more similar to R data frames and Pandas data frames. Those were the two sources of inspiration. And since then, all the other libraries are basically migrating to data frames. So although the RDD API is still there, you can use it, the DataFrame API is what is recommended and what all these libraries accept their input data in, because it's much easier for users to use them. And you can easily switch between these components, especially when they're all using data frames. You can basically use Spark SQL to read data or like query data, and then you can pass that data frame to MLlib and build a model off of it, and then pass that to a Spark streaming application and like do some real-time work with it. This is another important aspect of Spark, and particularly important when it comes to SparkR. Spark is a member of an ecosystem and is actually has been very much welcomed by the ecosystem. There are a ton of applications that are developed on top of Spark. Many other data-related companies have ported their application to integrate with Spark. Basically every environment we know of, Spark can run in. These are basically the cluster computing environments, and there's a module to import data from most other systems. So there are many data sources. So Spark is becoming like the core engine where you can read data from different sources and give it to different applications. And a lot of the companies are actually behind this, as I said. These days, every release of Spark has more than 1,000 contributors, and there are large. Some of these companies are running Spark on very large clusters. There are a lot of Spark talks. Most of these meetups, as you know, are recorded. Spark summits the videos are all online. I encourage you to go to sparksummit.org, or there's also another website called Spark Hub, which tries to gather documents from different sources. Anything related to Spark is tried to, Denny kind of leads that effort and makes sure all those are available in one place. Okay, so now let's get to Spark and R. But why? Before becoming a software engineer, I was a data scientist at Apple, and R was the primary language I used day to day for my job, and I loved it. And I talked to other data scientists, and it seemed many other people also really liked R. The reasons were obvious, but if you try to compile a list, it's open source. You don't have to pay a license fee. The language is very dynamic, and the environment is also interactive and dynamic. These are both important when it comes to interactive data science. There's a rich ecosystem of packages. Any algorithm you think of, you can find an R package that implements that. And for me, one of the key features was the powerful visualization infrastructure. The infrastructure helps in the sense that there are many packages that take advantage of the infrastructure. So that I haven't been able to find anything close to it. Finally, the DataFrame concept turns out to be a powerful one, the right choice for data science and data manipulation. And finally, one of the reasons is many schools are now using R to teach statistics, and every year the R users are entering the market. So they become data scientists, and as a result, R is popular among data scientists. With all those great things, we all know some of the limitations that R has when it comes to performance. The language is dynamic, which is great, but that dynamic nature makes it difficult to optimize the runtime. For example, in a loop, if you're running a loop in R, the runtime cannot assume the type of the loop variable is going to stay the same throughout the loop. It can change. And data frames need to fit in memory, so that also is a limiting factor. And the most popular runtime, which I assume most of us are using, is single-threaded. And so you have to do special things and use other packages to parallelize on a single machine. So with those great advantages and these limitations, what would be the ideal for me? When I was an R user, it was ability to seamlessly manipulate large data with R. It means like take advantage of R's flexible syntax, the packages ecosystem, the environment, and then in addition, being able to scale it up and out. By scaling up, I mean being able to run it on a very large and beefy machine, take advantage of lots of RAM and many cores. And by scaling out, I mean if the data doesn't even fit on a single machine, we need to run it on multiple machines. And finally, this was always a pain point for me, reading in data. In real world, data is stored in different formats, not always is in CSV. So, sometimes converting them to CSV to be able to comfortably read them in R was also a challenge. So, with that introduction, I think SparkR is in a great position to solve those problems. Like it's a great addition to the R ecosystem. What it is, it's an R package that is distributed with Apache Spark. So that's one of the things that I think should be fixed over time. The SparkR package should eventually become a package in CRAN, hopefully. It provides a front end to Spark from R. Basically, it exposes the R data frames to R, and exposes Spark data frames to R. And as you know, Spark data frames have all those great features. They're distributed, they don't have to fit in memory, and they're resilient. And also, with SparkR comes a number of functionalities and methods for easy transportation of data between R and the Spark JVM. So with that, you get best of both worlds, and that's or at least that's the goal, and that's what the SparkR development community is trying to achieve. Okay, so this is my illustration of SparkR architecture. This is how I see the world. And this basically is a Spark cluster plus SparkR. A Spark cluster consists of a driver, which is a machine that runs the driver process, the JVM process that calls itself the Spark driver, and a bunch of workers that also run, JVM, and they are running the worker processes. In the driver, when you're using SparkR, there is an R process that talks to the JVM, and it uses an object inside the JVM. Actually, it's a server. It's like a local server called RBackend. RBackend opens a local socket and listens on it, and the R process using the R packet, SparkR package, talks to RBackend over the socket, and that's how you write your code in SparkR in R in the R process, but the actual things happen inside the JVMs of the driver and the workers. So a few things to note is that there is no worker process there is no R process in workers, and because of this architecture, you get integration with all of Spark's data sources out of box. Okay, so we'll get back to this, especially if you have any more questions. But I'm going to do an overview, very broad overview of different APIs in SparkR. I kind of classify them into 6 categories or buckets. The I/O API is basically the hook for calling Spark's data source API or to read data into a data frame, and by that I mean Spark data frame. There is API for caching, which controls where the data is stored in memory or on disk. There are some utility functions, and these are very similar. The signatures is very similar to what you're used to in normal R. MLlib, which is Spark's machine learning library, is being ported to R. So far, the most important one that has been ported is GLM. There's DataFrame API, and these are kind of inspired by dplyr functions. So they're very similar to dplyr. And finally, you can use SparkR distributed data frames as tables. So you can register them as a table and then use these functions to query them in SQL, the SQL category of functions. Okay, so among all these, basically to get a good handle of the API, the first concept you need to know about is the SQL context. Basically, the SQL context is going to be your interface to all of Spark functionality from R. And the way you create it is by calling SparkR SQL.init. There is another object called the Spark context in the R process, but that's not, the reason I don't mention it is that you don't interact with it a lot. You only need it to create the SQL context, and it's on its way out in SparkR. So because no one needs to interact with it in SparkR, it doesn't even need to be exposed. So from now on, when you get your SQL context, you just use it in all the functions you call in SparkR, and it knows which server to talk to and whatnot. Okay, so as an example, here I take that SQL context object, give it to read.df, probably the most important data I/O function in SparkR and specify some other parameters and read data into a data frame. And this is a Spark data frame. It's distributed. And I can save it to disk as well in different formats. There's also API or functionality to move data between the R process and the Spark JVM process. The two important ones are the create data frame and collect functions. I'll tell you what they do. So if we kind of high level go back to our architecture, with read_df and write_df, you can read data onto the workers. So basically nothing happens really in the R process. So basically when you use them, data is read from distributed storage. And with collect and create data frame, things happen between the R process and the JVM process. With collect, you take data from all the workers, collect them on the driver machine in the JVM, and then serialize it over the local socket and transport it to the R process. So you end up with a local R data.frame object. And the opposite is create data frame. You give it a local R data.frame object. It sends it to the driver over the local socket. And then the driver JVM process will ship it to all the workers, distribute it for you, and then you get a Spark distributed data frame. Right now, yes. Your R process, because that socket is a local socket and it's not configurable, so we can't talk to a remote JVM process. Okay. Just kind of briefly, these are also important functionality when you are using SparkR. You can use persist or cache to control where your data resides. It's kind of, I think they're important because when I use SparkR, I'm mostly in the mode of doing exploratory analysis on large data, and I want it to be interactive. And for that reason, after I load my data, I put it in cache, so every subsequent query happens within a few seconds, and I don't have to wait minutes. So basically, cache is equivalent to persist to memory only. You can look up the documentation about the definition of all of these. Yes? Mm-hmm. In terms of what? Like what is the frequency? Okay. I see. So one thing. So let me repeat the question for the recording. What if the data is changing every few seconds? How could we analyze it with this architecture? The way that would work is you can have a Spark streaming job that ingests the data and creates a Spark data frame and updates it every few seconds or every second or so. And that data frame, as I'll show you, can be registered as a temp table. And then in SparkR, you can interact with that temp table, convert it to data frame and use it. That's actually a very common use case for people who want to ingest live data. Okay. DataFrame API. The initial idea was that basically SparkR's DataFrame API should behave exactly like R's data.frame. And as a result, the dollar is implemented, bracket is implemented, some of the names and dim and head, those well-known functions are all implemented. But this is not a complete set. So there are still some functions that you can call on local data frames that you can't call on Spark data frames. But that's one of the goals. It would be ideal if you could interact with the Spark data frame without even knowing you're interacting with it. But even with these and the other ones that I'll show you, it has happened to me that I forget that I'm using a Spark data frame here, and I pass it to a package, and it says, I don't know how to deal with this object, and then this is a Spark data frame, and then I collect it and then give it to the package. MLlib, as I said, GLM is the most the first and probably the most important functionality that has been exposed to SparkR. This is an area where the R community can definitely contribute to Spark by exposing more functionality from MLlib to R. And this is an area where more opinions would also be welcome because, kind of as a side note, the MLlib API in Spark, both in Scala and in Python, and as a result in Java, follows the pipeline paradigm, which is borrowed from scikit-learn. It makes perfect sense for Python users because they're used to scikit-learn, and it makes sense for Java and Scala users because they're comfortable dealing with objects. So you create a pipeline object and you modify it, and then you tell it what the data object is, and you call fit on it or transform on it, and it just runs the job, and you get the model. That's the essence of it. That is not the familiar model for R users. As a result, when GLM to SparkR was being designed, we thought we should expose it in a way that is natural to R users. Therefore, we implemented a formula parsing subsystem in Spark that gets a string, an R formula as a string, and then parses it and then constructs a pipeline using that. So basically, R users can now use their familiar format. However, it would be very helpful if we could learn from the R community what is the canonical way of calling a lot of these machine learning algorithms. So that's somewhere where your opinion would be very valuable. Okay, so last category of APIs is SQL, and as I mentioned, you can register a Spark data frame as a temp table. Basically, a data frame is a table. Like they're just very similar. I'm talking about Spark data frame, and there's a function called register temp table. You give it a data frame and you give it a table name, and from that point on, you can write SQL queries that talk to that table. And behind the scenes, Spark basically gets your answers from the data frame. And this functionality is particularly useful if you want to move between languages. For example, if you have part of your application implemented in Scala and you want some other part of it done in R, this is common because in some companies, in some environments, the data engineers prefer Java or Python and data scientists prefer R, and they can work together with this. The data engineers can build the pipeline. By pipeline, I mean the data pipeline in Python or Java or Scala, and then register it as a temp table, and data scientists just start working with that temp table, or vice versa. Okay, so I can take a few questions and then do some demos if there are any questions. And throughout the demo, you can also ask me any other questions. Yes.
So where does an R user go to submit his opinion on how things ought to work?
Oh, that's a great question. I'll actually. So the best place where discussion happens. There are some SparkR developers here in the room actually, but the best place to go would be Spark Jira, and here you can find tickets related to SparkR, and you can list them. There aren't that many actually. And look at them, see if there is already an existing ticket for what you're looking for. If there is none, you can create one, and in the comments, people start discussing. That's where the discussion starts, and usually the design happens. And when someone feels like they want to write some code, they take one of those tickets, submit a pull request to Spark, and in the pull request, also there's a lot of more detailed implementation discussion happening. So both places are good places to look for discussions. So if I search for SparkR, you can find basically SparkR related pull requests among all of the pull requests. While I'm on this page, let me show kind of the structure of the code. Let me zoom in a little bit. Is it visible behind the room? Yeah. So basically, there is an R directory, and this is the GitHub mirror of the Apache repository of Spark. There is an R directory where basically all the R code is located, and there's a README you can read. And this is basically an R package. If you look at any R package, you find similar directories. And here you can search for DataFrame.R, and basically this is the implementation of the SparkR DataFrame and all the functionality. Explain and whatnot. So you can submit pull requests against this GitHub repository. Any other questions? Yes?
When you call register temp table, at that point, is the object available outside of the context that was created?
No, it's available only from that SQL context. However, multiple processes can share same SQL context. Basically, the way it works in SparkR, if there is already an existing SQL context, when you call SparkR SQL.init, it will try to retrieve that. So you'll be talking to the existing SQL context. There's a little bit of attention you need to, it's a little bit tricky. You need to make sure if you want to do this across languages, across processes, just make sure you don't create two instances of SQL context. It's not, it's a little bit tricky.
So in two developers working in two different languages collaborate in real time?
Absolutely. Yes. We do that all the time. Okay, so let me, it's kind of related to this part about contributing. Show you, for those who haven't started with SparkR, show you this. If you want to start playing around with SparkR, you can start doing that on your laptop. In fact, there is some benefit to using SparkR even on your laptop. Because of the multi-threading thing, if you have a multi-core laptop, which most of us these days have, you can get better performance with very large files with SparkR than normal R. Yes.
Question, you said that the R process only runs on one machine. So don't get any distributed feedback from SparkR cluster. My R code is distributed.
Well, your R code is interacting with. So the question is, only one R process, and that's on the driver machine. How are we taking advantage of the distributed nature of Spark? The actual work is happening on the workers. The actual data is residing on the workers. From R, you just tell Spark what to do with it.
If I want to write an R function that maps over all this data, it can't be exported to the worker code.
No, yes, that's correct. Right now, that part is kind of missing. There's the proposals on how to distribute an existing R function. Actually, there's a JIRA for it, and I encourage you to go take a look at the proposal and voice your opinion. But yes, so far the way it has been is SparkR has been used for manipulating and ETLing large data, and for that people are using the functionality that is already implemented in Spark SQL and exposed to SparkR, and MLlib and exposed to SparkR. Yes?
Do you think that the RDD functions like map and filter that were no longer exposed when SparkR was brought into the Spark process, do you think those are ever going to be exposed, or are those just going to go away?
Well, there is never, they say never. In fact, when SparkR project, which was a research project at AmpLab, merged into open source Spark, for a short while in open source, in the master branch, there were the RDD functions, and then the community decided to kind of, for now, hide them.
The question is it just for now, or is it pretty much don't touch them because they could go away?
They could go away. Yeah, the reason they're hidden is that there's no guarantee that they'll stay around. They're not part of the supported interface, basically. They're not exposed interface. But as I said, there's active discussion on what should be the interface for distributing R functionality. There's a proposal. It's an interesting one. I encourage everyone to go read it. There's a JIRA about it.
UDF one?
Yes. There is some active members of the community think that is a much more manageable and useful interface than the RDD for an R user. Okay, so on your laptop, if you want to get started with SparkR, I encourage you to go check out the latest version of Spark. You can check out Master, which is right now 2.0 branch, and build Spark. That will be done using Maven or SPT. And then after that, this is the tricky part. A lot of people stop here. You need to run this script called install dev. And what it does is it will build the SparkR package. When you run this, you might run into some missing dependencies, and it will tell you what dependency is missing. You can install it and then run it again until you get a success. And at that point, you have the SparkR package installed on your machine. Then you can call in the bin directory SparkR. That will launch an R process and import the SparkR package into that R process and create the SQL context for you inside the R process. So you're ready to go. I'm actually going to show how that will work.
Has to be done every time
No. So the install dev doesn't have to be done every time. Only if you modify SparkR or you pull in new commits from master and you want to get those in your R package, you've got to rebuild the R package. Absolutely. Yes, absolutely. So let me show how that will work. All right. I want to make sure everyone can see this. Is it readable? Okay. So I go to, and I'm on master. So all I do is I call R, or I can go to R directory and call install dev. This will basically compile build the SparkR package for me. And it's done. Now I call bin SparkR. Okay. When you see this, it means the R process is running. The Spark driver is running, and your R process is connected to it, and you're ready to go. And this is R, basically. You can do the universal test of 1 + 1. So now let me actually do a little bit more.
So is this using in the background your current R that you have installed, or is this?
Yes.
Okay.
I could have done this in R Studio or any other R environment. Just you call install dev. You have a SparkR package installed on your machine. In your R Studio, you import SparkR, and then just follow the documentation. You can do SparkR SQL.init, and that will give you a SQL context. But if you call that script from here, it basically does create the SQL context for you. Basically, I call the script that does all that. Those steps. You can call that script from your R Studio as well. Okay, so let me bring up this. So here's my SparkR on my local machine. I have a fairly large file, and this is just for the purpose of a demo. I'm not trying to do any performance benchmarks. I have downloaded about a 1 GB size file to show you how easily I can, this is fairly large when you want to do it with R, to just show you how I can easily interact with it. So, to save time, I'm calling read.df and give it the SQL context. The source is a CSV data type, and the path is where I've stored my file. And delimiter is or separator, as R calls it, is a tab, and I want to read the first line as a header. And I just press enter, and I get a data frame. So df is a data frame, and it already, basically it found that the columns, is it readable? Found the columns in my data, and I can start using it. So I can basically call this as a temp table. It's a, one file about 10% of wiki edit dump. So I registered as a table called wiki. Now I can start interacting with it. So let me bring another. Yes. Yes, so if I try to collect or bring down all of this data to my R process, I'm going to have two bottlenecks. One is that all of that data is going to go through that local socket, which is not very efficient, and I'm going to go through, get serialized and then deserialized at the other end. Second, I'm back to the single process, single thread R world. So I don't want to do that. So here's how I do it, how I manipulate and explore large data with SparkR. That's exactly what I want to show. I'm going to do some analysis and some aggregation or sampling on that data before I visualize it or do other things with it. I do that part, the heavy lifting part, in Spark, and once it becomes small and manageable, then I bring it down to the R process. So let me show you that. So I'm using my greeter package. It's very cool. It basically allows us to nest multiple functions with much less hassle. And I'm going to call a SQL function and do an aggregation. So I'm going to count the number of users and user from this table. Let me bring it up so everyone can see. Table wiki, and I group by user and order by count, descending, and I limit them to 5. So what this does, it basically tells does it select?
Order by count?
Yes, order. Okay, so let me assign it to a variable, counted. So this is now a new data frame. Nothing has happened yet. I just told Spark that you can construct a new data frame, but with this transformation, and I expressed that transformation using SQL, and assign it to a new variable. Now, if I collect it, the reason I can collect this is I've already limited it to top 5, right? So I know it's going to be 5 rows and 2 columns. So I collect it, then Spark starts, crunching the data and getting my results. And these are like the top users in terms of number of edits Wikipedia data set in that file that I had. So at this point, when I do this, I call it top users. Doing it again. And I call str top users. This is an R data.frame. Whereas if I do str counted, it's going to materialize it again. That is a Spark data frame. And 2 different types of objects. Any questions so far? I'm going to do another demo with larger data. But any questions so far about how to get started on your laptop?
You really have to serialize the data frames, capital D data frames?
Probably not. I think str tries to pull things, and then Spark says, "Oh, this is accessing something that I need to materialize." Yes.
Not sure if I got the intuition behind why do you call it the
here's the idea. The SQL context encapsulate all the information needed for the R process to communicate to your JVM. So you could theoretically have two SQL contexts. One talking to one cluster, another talking to another cluster. I'm not saying that will work out of box, but the SQL context basically tells SparkR, hey, now talk to this cluster or talk to that cluster. You know, if you have only a single, if you hard code the assumption there's only going to be a single Spark driver, then we could make the SQL context implicit and hide it. But okay, so back to slides. So the first way, most common way of trying out SparkR was that. After that phase, most people who are dealing with really large data want to try it for their real application. They want to try it on their cluster. In that case, you need to run a Spark version 1.4 or above. There are quite a few folks out there who are running Spark 1.3 and 1.2, unfortunately. So they can't use SparkR. SparkR was added on that version. So that's the first step. So talk to your operations team or Hadoop supporter and ask them to upgrade you to some distribution that has at least 1.4 Spark on it. Another way is you can use to actually get the latest version of Spark. You can use one of these cloud providers that offer Spark as a service. One of them is my employer, Databricks. We actually have a 14-day free trial. You can sign up at databricks.com and try out SparkR with basically the latest version of Spark and SparkR in our product. Or you can also send me an email, and they have something interesting for you. Okay, so let me show how I can use SparkR to crunch much larger data. And for that, I'm going to use Databricks. So this is it too big or too small? Perfect, great. Okay, so this is our product. We call it Databricks, and this is what we call the workspace. And in the workspace, I can have a bunch of clusters. So I've already a cluster for myself and called it Hossein demo. It has, as you can see, 14 workers on Spot instances. So we don't pay a lot of money for it. And total 450 gig of RAM available on those 14 instances, 14 workers. So I'm going to use this cluster and show you some more interesting data analysis with SparkR. So I go to my home directory, and I go to Seattle R Meetup and create a notebook. Call it demo. It's going to be, I can choose the language to be R. And I choose my cluster and start it. Okay. So I have already stored a fairly large data set. It's from the songs data set on S3. Because I didn't want to reveal my keys to you guys, I have mounted it. So I just list the mounted, I just list the mounted directory, and that'll show you the files. So you can see there are fairly many files here. This is a public data set called the Million Songs data set, and I've kind of cleaned it up a little bit and picked the interesting columns and put it there. Now I'm going to load this data into a SparkR data frame. So I'm going to use readdf. I already showed you this. SQL context is already provided to me, just like the R shell in Spark. And the source, it is in CSV format. And the path is where I just listed it. And it is tab separated, so I pass that just to be consistent. And It has one line as header. Every file actually has one line of header. And I wanted to do the smart job of inferring the schema for me. This is basically using a data source called SparkCSV. Developing it, I tried to make it very similar to R's read.csv data function. So it has fairly similar functionality, although the namings and the arguments might be slightly different. So this will basically look at all my data and find the best schema that matches the data in terms of types. So it needs to read all those files once and scan every record at least once to find the best schema. And this will take about 2 minutes. I can take a question while this is running.
Define schema, what exactly do you mean? Because normally in relational databases, we have the connections between as schema.
Oh, so the question is, what do we mean by schema? Here by schema, we exactly mean what are the column names or field names and what's their type.
It's what pretty much the STR does.
Yes, similar. Although I think STR does a little bit more. It provides you some statistics about some of the fields or most fields as well. Yes?
I think right now, if you have a column that has, like for example, integers and then NAs, it'll infer a string.
Yes.
Is there any plan to read from CSVs and interpret NAs as null?
Yes, there is a JIRA that there's actually someone from the community actually had a great suggestion in terms of how to organize the different options for NAs and nulls and NANs in different types of data. Spark CSV actually in Spark 2.0 moved into Spark, so now it's built in. You don't have to use an external package anymore. And that JIRA is open for 2.0, so I'm hoping for before 2.0 is released, that thing will get done. So hopefully we'll have much better support for specifying default NAs and nulls and missing values and stuff. Okay, so this is done. Now I have, if I can find my mouse, I have data frame called songs. If I type it, you can see this data frame and you can see the schema. I can actually show the schema much better. There's a function called print schema, SparkR function, that shows this tree of like what's the name of each field and what's the type, and is it nullable or no. That's exactly what we mean by schema. Cool. Now I can do other interesting things. First thing I'm going to do, because I'm going to explore this data and access it and manipulate it multiple times, I'm going to cache it. So as simple as calling cache. This doesn't do anything. You just tell Spark the first time you touch the data again, don't put it back on disk. Keep it in memory. Now, in order to force Spark to touch it, I'm going to have it count the number of rows. So let's do that. Again, it's going to touch every record in every file, and that's going to take about 2 minutes, or 1 minute, I think. So I can take another question. Yes?
With one of those things versus like 2 Spark jobs, can you actually open that up for one of the previous ones to get more information?
Yes, absolutely.
Like that one?
Yep. Job 1, job 2. You can even click here and see the Spark UI for it. This is the if you run Spark on your laptop or on your cluster, you get a Spark UI. This is the same thing. Just put it in an iframe there. Cool. All right. Get to our here. As it's running, I can see what it's doing. Okay, it's done. So it took 54 seconds. Now it's cached. So what happens if I call count or count number of rows again? It should be faster. And it is. It's about 1.8 seconds. So our caching is working. We're good. Okay, so first thing I want to do, I want to register this as a temp table. Another thing I usually do on my day-to-day SparkR usage. Now it's a table. And from now on, I can query it in SQL. So I can say select star limit 10. And this will render a table because I just queried a table. Right? Okay. So let's do some more interesting stuff using the DataFrame API to show what things are possible. Again, I'm going to bring in the McReader package. In the notebook, I'm installing it and then loading it right away. So that's done. And from now on, using McReader, I can do much cleaner syntax. So I'm going to count the duration, the average duration of songs over time. So it is songs sent to group by function. I'm going to group by year. And then I send the result of that to an aggregation function, average, for duration. Since it's going to create a default name for that, I want to rename it. The name is average duration, and I just want it to be called duration. Okay. So I run this. Now let's get the top fields and inspect it. See what we got. Here again, we're running 2 jobs and so we see a duration value for each year, and these are the top 5 rows. Okay, now let's plot it. So bring in another library. Exactly. Someone said ggplot. And now I'm going to plot it. So let's also do this. So that we get perfect dimension. So I do ggplot, and year, duration, blue, the American spelling. Okay, so let's run this. What do we get? This error I swear I get it a lot. Because I forget, I am using Spark DataFrame, not an R DataFrame. Basically, ggplot tells me I don't know how to deal with data of class DataFrame. Actually, a very nice error message. I wish all error messages were like that. That's easy to solve. I just collect it, and I know I can collect it because I've already aggregated my data. It's not going to blow up my process. And no, in your namespace, actually, they're all in the same namespace. So, okay, so this is the plot we get. It doesn't make sense. And the reason it doesn't make sense is that there seem to be songs at year 0. And that is probably some bug with the data, and we are all familiar with that. We know there's no perfect data set, so we got to take care of that. Taking care of it is very easy because we can interactively change our query and run it again. So what I'm going to do, I'm going to run subset year greater than 1930. Run this again, and go all the way down and run this again and see what we get. There you go. So you can see the song durations are changing over time, especially during 70s something happened. Okay, so how are we doing on time? Okay, so let's, you guys, yeah, question? You can get a well, it will take forever, and then eventually you get a failure, yes, if it's too big. Exactly. That was perfect. exactly what I'm trying to get across. That you can do your big data, heavy lifting with SparkR, and then just collect it, and then do the rest of your work inside your R process the way you're used to do. So MagReader, all it does, it just helps me, call multiple nested functions inside each other. That's all it does. I believe dplyr, the way it gets its nice syntax, is using MagReader. So because someone mentions SparkR functions, this is the page for the latest version of the latest release version of SparkR. You can see all the functions here and their documentation. So the way to get there, for those who aren't Spark users, go to spark.apache.org, documentation, latest version, API documentation, R, and you get to that page. There. Okay, let's continue with our large data exploration. So this was just a simple average, but we all know what can go wrong by just looking at the average, right? You might get fooled. All right, let's do a little bit more detailed look at our data by sampling it. Obviously, this is 1 million data points, and I can't plot 1 million data points. So I'm just, in order to get a good feel of individual points, I'm going to sample it. So let's run it. This basically, same thing. Oh, sorry, I didn't bring in the right line. So here what I'm doing. I'm again subsetting years greater than 0, and then I'm sampling. Let's actually make this 1930, and then I'm calling sample. It's another SparkR function with replacement false and 0.005 fraction. Okay. Now I can see how many rows I have in my songs. It's 2,500. Now, because it's 2,500, I'm comfortable plotting it. So let's do a plot. This time I remember to collect it. Here, duration. And because I want to see the spread, I do a smooth fit. And this is what we get with sampling. So I'm not totally satisfied with this, so I'm going to change this to jitter, because all the songs with the same year are aligned perfectly on that year value. And I'm going to make them a little bit smaller. And actually, let's just make them smaller. See how they look. I'll zoom out a little bit so the plot fits in the page. Well, maybe things we need. It seems we need to make it a little bit more transparent. Yeah. So this is what it looks. Okay. So this is sampling your large data from using SparkR and then plotting it. So another. Let's just similar analysis. I'm going to say, what are the top artists? Similar to R Markdown, you can use Markdown here in the notebook. So let's call artists. It's going to be songs. I'm going to copy this. And I will group by artist name, and I will count them, and I will arrange them is autocomplete. That helps a lot. Count. So this will give me a number of songs for each artist, and I can do a head on it and see what are the top top artists with most songs in this data set, at least, if not at all. And there you go. Michael Jackson is #1 with 194 songs. So let's assign it to a variable called top artists. And now I'm going to do another thing. Let's see how loud are they. Because there is a column in our data called loudness. So I'm going to just look at that. And songs. And I'm going to just filter those artists that are on the top list. And I'm only interested in this. Is the subset signature is very similar to normal subset in R, but this is the SparkR subset because we are operating on SparkR data frames. So I only want artist name and loudness, and hopefully I typed everything correct. Now I can plot it. Let's see how many rows it has before we attempt plotting it. You always want to watch out for collecting a very large data set. Thank you. So that's feasible. I can plot that and collect artist songs. So I want artist name and loudness, and I do a box plot for it. And this. Let's make this plot really pretty. And this is how it looks. So they are quite different in terms of loudness, at least in this set.
How are you able to use the graders in the SparkR without collecting it?
McGreader, all it does, it takes the syntax you provided and just rewrites it so that there are nested function calls. It doesn't know what function you're passing. I could be using McReader with my own functions. It doesn't care about the actual function, where it comes from. Yes? Oh, I can write an R loop here, just like this is, here again, just to emphasize. So the question was, how can we do looping and like generate hundreds of plots? Let's say. There are two things happening in my notebook. My interactions with distributed data and things that I do in the single process R environment. My interactions with distributed data are only those things that I use from SparkR package. Everything else is normal R. So if I write a loop, or if I do a for loop, or if I do an lapply, or if I do something else in my RStudio or local R process to loop and generate hundreds of images, I can do the same thing here. In each loop, I just run the same thing. Only thing to watch for is not to collect large distributed data into your R process. Like, let me give you a specific example. If I wanted to do this box plot for every variable in that in this data set, what I would do here, I would basically do a for loop over the elements in my schema, which I can already look at. And in each iteration of that loop, I run that aggregation, collect the result as a normal R data frame, and then plot it. Exactly, exactly.
So your laptop memory is the collect is limited to what is on your laptop. So that is the only thing that you do.
Yes.
So do you need to keep clearing it?
Yeah, you can remove memory from your environment. Yeah, you can do that if you run into memory pressure on your R process.
But you can't, like, for example, you can't run Outline on your Spark database. That's not.
Yes, yes. Someone needs to implement an lapply that takes a Spark capital D data frame.
And I don't know if you're familiar with the development sphere for Spark overall. Is SparkR something that's heavily contributed to compared to like ML and those other major branches or Spark?
I can say that SparkR is not the most active component. And that's entirely up to the community. The other components are active because more people submit code to them. I think there is kind of a disconnect between the R community and the Apache Apache Spark community, and that's what I'm trying to, bridge. Like, tell the R community there is this thing, there's a GitHub repository. Please join and contribute.
Are you personally just focused on SparkR now?
Not 100%. I do a bunch of things, including some work on SparkR. Any other questions? Yes.
So we sample the data for plotting purposes, but if we want to know the quantile Hossein distribution of the entire 1 million data points, is it possible with a statement in this interface?
Basically, you want to count, right? Do some frequency counting to find the distribution, right? So you could do it with a bucketize and do group by with that bucket and count. Yes. Yes.
Say when the SQL context that we're addressing here is no longer available, is it tied to the process that created it?
In R, you can terminate the R process. In SparkR, you can terminate the R process, open a new R process, and get access to an existing context as long as the JVM process doesn't terminate. So it depends how you're managing the life cycle of these two processes. If you launch your JVM process first, and then launch your R process and have it connect to the JVM process, basically, and to get the existing SQL context, then you can kill the R process and have your SQL context, there, still running. But if you launch the JVM process from the R process, the way the SparkR script does in open source Spark, then when you terminate the R process, the child of it, which is JVM, is also going to be terminated. So you lose your SQL context.
Do it the first way if you want another actor to improve the results of
Yes.
You have two R's connecting to a single JVM.
Absolutely. So let me show that. So I'm going to create another notebook here. And choose R, and then connect to the same cluster. And in my SQL context, I created a temp table called songs table. I can just query it. Because it's a temp table registered in that SQL context, any R process that talks to that SQL context will get it. Yes?
Just curious, how big was that songs folder that you started with?
Oh, in terms of the size in bytes? Actually, don't know this subset because I selected a subset of the columns.
I'm just talking about what you started with, before you started.
Oh, the original one, yeah, 100 gigs. But I'm not very sure about the. Yeah, I'm not sure. In terms of, so here I obviously wanted to choose a data set that is not too big and not too small. In practice, at Databricks, we do our own data science using SparkR, and we have tables that are terabyte size, and we run daily jobs on them. They're not like some of the jobs like take hours on terabyte data sets and they finish. So I can basically here, just to show you, I can here you can create a job. I'm just gonna say songs job, and choose a cluster. Either I can choose to start a new cluster or run it on an existing cluster, my demo cluster, and then choose my notebook. Yeah, there you go. Seattle and demo, and then have it run according to a schedule, like say every hour or every day at that time, and have it run. And this will take that notebook, run it, and then if it wants to save its results or whatnot, it will do that. So this job is now running, and I can view it as it's running. Yes?
Do you think this which one is faster and efficient? First, using the temp table and then we can create a SQL query. The other one is from the data frame. We can create another data frame, find a group by or filter or whatever. Do you think this is what is
They're the same. Under the hood, they translate to the same thing, because whether you specify your query as a SQL statement or you specify it in terms of DataFrame API, they go to a SQL optimizer, a query optimizer called Catalyst, part of Spark, and it will construct the logical plan for it, and then it will translate and optimize that to a physical plan, and then execute that physical plan against the underlying RDDs. So basically, all of this is manipulating RDDs under the hood. We just do it much, much nicer and more efficient because we're doing the optimized transformations.
well, Python is the same way of optimizing.
Yeah, every data frame from any language, any data frame interaction goes through Catalyst. There's one exception in Python. If you use user-defined functions that are written in Python, there's going to be one step of serialization of data to the Python process to apply the function, and that's not as efficient. But if you don't use Python UDFs, it's going to be as efficient as you do it in Scala, as efficient as you do it in R. I really want to encourage all the R community to contribute to SparkR. Cool. Thanks a lot, everyone. And it was great.